Log on, tune in, find out. Another good idea from Cambridge.
So the first talk of the day is
Okay, thank you. Okay, so I'm giving an introduction to algebraic stacks. So today I will just, I'll try to define what stacks are and what algebraic stacks are. So let me start with the definition. A groupoid is a category well, all morphisms are invertible. So let me just give some examples. Okay, so one good example to keep in mind is the fundamental groupoid. Of a topological space. So let's call this thing capital Pi. So the topological space is X. So that's the set of all triples X, gamma, Y, where X, Y are points of X, and gamma is a homotopy class of of paths. Homo. So in this case, the objects of the category are the points of X, and so object is X, and all the morphisms. So all the morphisms of this category are given by pi, and I usually abbreviate this kind of groupoid by a diagram like this. So this is a set of all morphisms, and this is a set of all objects. And there's two maps, the source map and the target map. This one sends each object to its source, like this triple to X, and this is the projection onto Y, the target. But there's more data. Right, there's the identity, and there's an inverse, and then there's a composition. But the way groupoids come about in stack theory is as follows. So the second main example is the symmetry groupoids. So we're all familiar with the fact that in mathematics, if you have an object, its symmetries are given by a group. I mean, the symmetries form a group. But what happens if we don't consider a single object, but a family of objects? Then we get not groups as describing the symmetries, but groupoids. So symmetry groupoids of families of objects, some kind of mathematical object. So let me just start out with some really, really simple examples. well, what do I mean by objects? So, for example, let's just, so I need to decide on some mathematical concept of objects and some kind of isomorphism between them. So, for example, let's consider triangles, by which I mean usual triangles in the Euclidean plane as you know them from Euclidean geometry. And the notion of equivalence is similarity. So if I just have one object, for example, an equilateral triangle, we get the symmetry group S3. But if we have, for example, a family of objects, so let's say an equilateral triangle and an isosceles triangle, so a family with two triangles, then the symmetry groupoid, well, well, there's an S3, so in some sense, well, there's two objects, and then there's an S3 as some kind of disjoint union with an S2. Or let's look at a more symmetric family. This is a family of four triangles. Let me draw it like this. So again, there's an isosceles triangle. No, sorry, an equilateral one. And three isosceles triangles. Let me label them like this: 0, 1, 2, 3. So, what is the symmetry groupoid in this situation? So this should be so my set. I have four objects. Sorry, this is supposed to look symmetric. So this is the set of objects in my groupoid. Right, there's these four triangles, and these are all the morphisms. So whenever I have an element of S3 which acts, I tried to draw this symmetric so it's clear how S3 is supposed to act on this picture. So if I take an element of S3 and an element of this set, so an element in this product set. So for example, so I pick this triangle here and an element of S3. If it's the reflection in here, that gives me a symmetry of this triangle. If it's, for example, the reflection in this, then it gives an isomorphism of this triangle with that one. So, what is actually symmetry groupoids of family of objects? So the morphisms set, that is equal to the set of all symmetry groupoid all isomorphism of one object with another object in the family. I guess I should have said that at the beginning. What is the symmetry groupoid of a family of objects? Just any isomorphism of one object with another. So, for example, an isomorphism of this one with that one because these two are similar, or a symmetry of one of these. Right. So those.
So an example with four triangles. lying in the same plane? Meaning, is the one that moves 2 to 3 the same as the one that moves 3 to 1? It's the same sort of rotation of the plane? Or are we considering completely separate developments?
Not sure I understand.
And in that case, also you should have a constraint union, right? It should look like the problem before, right?
Well, this, okay, as categories, so as groupoids, this groupoid here is equivalent, well, equivalent as categories, is equivalent to the previous one. I can just pick, well, I don't know, pick these two here. And then restrict to all restrict the family of 4 triangles to this family of 2 triangles, and then just consider all the isomorphisms of these 2 things with each other. And I get the previous one. But this one is well, I don't want to say any more right now. So let me now come up. So this is the abstract definition of groupoid. Now I want to define algebraic groupoids. So but I can define at the same time not just algebraic groupoids, but I can define groupoids in all kinds of geometric categories. So for example, I could say analytic, or maybe differentiable. Well, so what does this consist of? First of all, there's schemes R and U, and then there's morphisms of schemes. So S and T from R to U. There's E from U to R, I from R to R, and M from plus a list of axioms, and these are supposed to formalize the abstract concept of groupoids. So where you should think of U as set or a scheme of objects and R as scheme of morphisms. And to describe the list of axioms, the most elegant way to do this is say, so for every scheme T, we get sets R of T. So those are the morphisms from T to R, and U of T. And I get induced maps. And so for every scheme T, this should be a groupoid as I defined it up there. So just a category where all morphisms are invertible. Right, so you can translate this into all kinds of properties of these maps here. If you want to define differentiable groupoids, for example, just replace the word scheme by differentiable manifold. And then you get this differentiable groupoid notion.
What do you mean by that RTUT with double F?
What do I mean by this? That is the morphisms from T to R. So that's, in other words, I think of every scheme as representing a functor. So this is in the t-valued points and u-valued points. Okay, so now examples of this concept here. So the stupidest example is if x is a scheme, and I take u is equal to x and r is equal to x, and all the maps are the identities. Then you can check that this satisfies all the properties. I mean, if I plug in a scheme T, then I just get a set. But what example of a category do I get then? Well, that's a category where there's only identity morphisms. There aren't any morphisms which aren't identities. So this is the first one. More generally, let's say U alpha is an open cover of X. Well, Zariski or et al. Then define U. The disjoint union of all these U alphas and R, the disjoint union over all the intersections. And then so I leave it to you as an exercise to figure out what all these maps S, T, E, I, M are in this case, and that this is a algebraic groupoid. Third example, so generalization of, well, or maybe not, well, yeah, generalization of the previous one. Okay. If I have any morphism e to s, so any morphism of schemes, I can form the fiber product. So whenever I write a diagram with two arrows like this, you're supposed to understand, I mean that this is a groupoid where this is the object space and that the morphism space. So this is R and that's U. So again, exercise to check that that's okay, here, fourth example, G is an algebraic group acting on scheme X, let's say on the right, and let's say sigma is the action map and P is the projection map. This is an algebraic groupoid. So this is called the transformation groupoid, associated to this group action. So you're supposed to think of so every point in the scheme which is acted on is an object in the groupoid. So here's maybe X. And then if I have a pair of elements, X comma G, that is considered to be a morphism from X to XG. So the source map is X. Well, haven't really. Okay, so this is. Okay. Again, you can check all the axioms. And last example is an equivalence relation. So R is a scheme mapping to U cross U. And if this is an equivalence relation, then we get an algebraic groupoid. Right, I get two maps to U giving me the source and the target map. So again, you can check that. Well, I guess all these examples 1, 2, 3 are examples of equivalence relations. So in general, I mean, whenever I have an algebraic groupoid, I can consider this map R into the product U times U. And if this map is injective, then the groupoid is an equivalence relation. But it's, right, so for example, this one is not an equivalence relation unless the action is free. Okay, so, I wanted to more examples. Some examples of symmetry groupoids. Well, over there I just talked about discrete families because I wasn't talking about geometry yet. So now I want to talk about continuous families, or families parameterized by schemes. So let's go into algebraic geometry. So let's look at elliptic curves up to isomorphism of elliptic curves. Let's see, and my favorite example of a family. So there's many nice examples, of well-known examples of families of elliptic curves, but as one example, so let's look at the Weierstrass family. So there's T, the parameter space. Let's say that's C2 minus the origin. This is the parameter space. And the coordinates are for some strange reason called G2 and G3 in C2. And then I define a projective scheme over T. So X is given by the equation, by the affine equation y squared is equal to 4x cubed minus G2x minus G3. So that defines a cubic, a family of cubics in P2 parameterized by T. Okay, I haven't thrown out the discriminants, so these might be degenerate elliptic curves, but that's okay. Okay, this is the Weierstrass family of elliptic curves. And so what is the symmetry groupoid? Of this family? So it will have, let's see, well, so you have to figure out, I'm given two elliptic curves in Weierstrass normal form, like this. What is the general isomorphism? When are two of these curves isomorphic? And what are the symmetries of the individual curves? And so you can, let me just give you the answer. You can convince yourself that this is true. So let's. So the symmetry groupoid is a transformation groupoid for the following C star action. So C star acts on T. So let me just write, so lambda acts on what am I doing here? Lambda 6. So lambda acts on G2 and G3 just by weights. C star acts with weights 4 and 6. And this action lifts. This is an action on the parameter space, and this lifts to the total space of the family. So now lambda. So the total space, well, they have x and y and G2 and G3. On x, it's lambda squared x, lambda cubed y. Well, we already know how x and G2. So here's. So my claim is that so every isomorphism of one elliptic curve in Weierstrass form with another one in Weierstrass form is given by an element, by non-zero scalar lambda in C star. It's given by this formula here. Okay. I mean, you can convince yourself of this. Say, first you have to prove that if you have an isomorphism of one such a curve with another, it's just given by a projective change of coordinates. Well, it has to preserve the point at infinity. Then this is just a affine linear change of coordinates. But then you notice that to stay in Weierstrass form, all you can do is multiply x and y by non-zero scalars, and then, I mean, you can convince yourself that I mean, both of those scalars have to be multiple of the common scalar lambda. And anyway. Right, so sometimes families are very symmetric, like this family with these four triangles. I drew them in this symmetric way, and then the symmetry groupoid is globally transformation groupoid. I mean, it is equivalent to something like this, which is not a transformation groupoid. But so it's not an obvious thing to see. You know, if I had drawn the family like this, it might not have been so obvious that there's a global symmetry in the symmetry groupoid, namely that's a transformation groupoid. Anyway, so the Weierstrass family also has this nice property. Okay.
Which one of those is the one called? Which one of those is the symmetry groupoid?
The symmetry groupoid is so this is the action, and then if I also put the projection, then this is the symmetry groupoid. Meaning that so if I have an arbitrary non-zero scalar and an arbitrary value of G2 and G3, that defines an isomorphism. Right, so the element lambda comma G2 G3, right? This is the isomorphism from X is an isomorphism from this member of the family to this member of the family. And lambda acts on the family by acting on x and y by that formula there. So this is sort of the universal symmetry, I don't know, of elliptic curves in Weierstrass normal form. Right, so every element in here defines a unique isomorphism of one member of the Weierstrass family with another member of the Weierstrass family, and therefore this is the symmetry groupoid of the Weierstrass family. The base of the symmetry groupoid is always the parameter space. Should I do another few examples of symmetry groupoids? Well, okay, I like the triangles anyway. Mike Artin himself is reputed to have said that if you study a stack of triangles, you can understand everything about stacks. So that justifies studying this thing. So if you go back to triangles up to similarity. So this is a differentiable manifold. So the differentiable manifold N, which is the following. So this is a set of all A, B, C in R3 such that the sum of A, B, and C is 2. A, B, and C are all less than 1. This differential manifold parameterizes a family of triangles. Because, well, the point ABC gives the triangle with where the lengths of the sides are A, B, and C. And I mean, okay. So what is a symmetry groupoid? I mean, these conditions are for the triangle inequality. What is a symmetry groupoid of this family? Well, I'll give you the answer. It's again a transformation groupoid. And in fact, you can find this this discrete family inside that family N as 4 points inside N, and then so the whole thing, this works just like that over there, just with all triangles, not just 4 representative ones. Let's do another example. So vector bundles is a mathematical way of formalizing the notion of family of vector spaces. So this is the same thing as family of vector spaces. So if E over T, let's say, is a vector bundle over the scheme T, what is a symmetry groupoid? Well, vector bundle, let's say the rank is fixed of rank n. Well, then all the fibers are isomorphic as vector spaces. And so whenever I have 2 points in T, well, the fibers are isomorphic, and then, of course, every fiber has a symmetry group which is isomorphic to GLN. And, well, let's see, so let me just throw. So the scheme of isomorphisms here's P1 and P2 are the two projections of the product onto T. I can pull back E via both P1 and P2, and then I get two vector bundles on T cross T, and then I look at the bundle of isomorphisms. So this is this is over T cross T. This is a GLN, principal GLN bundle. Anyway, and so this, and then I can map that in two ways to T. This is a symmetry groupoid. Okay, I want to get a little more formal. So far I've assumed, well, I've in these three examples, I've just assumed that you know what the notion of a family of elliptic curves is, or what a family of triangles is. Of course, you have to figure out some kind of mathematical definition of what that is, or what vector bundles are. So in general, to talk generally about these things, I need to introduce an abstraction of what are families of objects. So to talk about that, I want to talk about categories fibered in groupoids. So let S, to fix ideas, let's say the category of C schemes, or if you're in, or you could, for example, say, or the category of differentiable manifolds, or the category of analytic spaces, your favorite geometric category. Now this is some kind of base category on the objects of S. These serve as the parameter spaces for families. I want to consider. And so a category fibered in groupoids so let me call it CFG for short, this is another category, and this is a functor. So it's a category X together with a functor to S. Such that okay, what are the axioms? So so this happens downstairs in S. If I have a morphism in S, and I have an object little x of the category X, and I'm going to draw a vertical arrow, meaning that under this functor, this object goes to that object. So I don't want to put an arrow because this doesn't happen inside any category, but it just means that X is over S. So whenever I have this diagram, then there exists y over t and this arrow from y to x, which lies over that one. Right? This morphism sends that arrow to that arrow. So this is the first axiom. And the second one is that if I have a triangle downstairs,
So the vertical arrow images are the functor from that space.
Hmm?
The vertical arrows in that square are the images under that functor.
yeah. So this notation here, I don't know. So x means if this is f, that's a notation. And I guess strictly speaking, I also mean that this arrow there lies over that arrow. So maybe I should also put some kind of indication of that map. So that one. Right, so for all white diagram, there exists the yellow completion. And so now if I have x sitting over S and y sitting over U and Z sitting over T, if I have this diagram, then I can fill that in uniquely. Right, so again, for all so if x sits over S, I will say that x is an X family parameterized by S. And that's what you should get. This is supposed to formalize, I'm giving general language to talk about families. So whenever I have an object here sitting over an object there, I just say that this is a family parameterized by that thing down there. So that's right. So it could be, yeah. Okay. And in this, and if I have a diagram like this, I usually write y is equal to x restricted to t. And you should think of this as pullback of families. Pullback of the family X via this morphism from T to S. You say, well, this, how can I use this notation? This makes it look like this pullback is unique. Well, it is unique up to unique isomorphism by the second property. I mean, just like pullback diagrams of schemes, there's always this, the pullback is unique up to unique isomorphism. Yeah. Okay. So this is just notation. And this is pullback of the family. So a CFG, so CFG formalizes the notion of family of mathematical objects which pulls back. So.
Are the maps from Z to Y and from Y to X also unique?
Sorry?
The maps from Z to Y and from Y to X are also unique?
Z to this map from Z to Y, that's unique.
That's unique.
Yeah.
And also from Y to X.
From Y to X. No, this is yellow. This is white, so it's given. So white is what's given, and yellow is what exists uniquely. So CFG, so. So CFG formalizes families of mathematical objects which can be pulled back. or restrict it to, if I change the parameter space, I get an induced family. Okay. Okay, now we need examples of categories, fiber, and groupoids. Okay. Now, what are these examples? Okay. So it's the stupidest one. If X itself is a scheme, we get so to distinguish it from the scheme X itself, I'm going to underline the X, but only for a very short time. Okay. So the objects of X underlined, these are morphisms of schemes, and the morphisms in X are commutative diagrams like this. So in other words, so X is just the over category of schemes over X, and this functor F just sends so F of T to X is T, and F of this diagram is just the first bit. In fact, so every scheme defines category, fiber, and groupoids this way. And a CFG, well, so if you have an arbitrary category, fiber, and groupoids over S, and then you have one of these guys, and you have an equivalence of categories which commutes with the projections to S. So this is an equivalence of categories. Okay. Excuse me? This functor here, it's given by this formula. Just project onto the first, onto the source. So when you have a category, fiber, and groupoids, so well, so yeah. This is the definition of representable. Let me remark that if this is a category, fiber, and groupoids, and S is a parameter space, so X of S, this is the category of objects over S. So those are all the objects of X that get mapped to S with morphisms which lie over the identity of S. You can check that because of these axioms, this category is a groupoid for all S. And if you have a morphism view, you can so by some vigorous making, the application of axiom of choice, you can choose for every X, for every family over every T, you can choose a pullback, and that defines then a functor from the category over T. So all families parameterized by T to all families parameterized by S. Pullback functor. And what did I want to say? So in this case, in this example, so X of T is what you usually is the set X of T. So the morphism from T to X. And so this is so the scheme X represents a functor, and this X underlined is just another way of thinking of that functor that X represents. Right, so this is basically so X. It's just a different way of thinking. Think of this functor as a category fiber in groupoids rather than a functor. But and you can think of a functor from S to sets as the same thing as a category fiber in groupoids where all the fibers are sets. So, but I want.
When you write that equality, it acts as like a point. T has automorphisms. Is it?
I don't know. No. Is this all the morphism from T to X? I don't know. Let me continue with these examples. So G, an algebraic group, and so BG is the CFG of principal G bundles. So objects. So right, this is this. So the objects, these are principal G bundles, E over S. So let's say they're on the right. So a principal G bundle is, well, it's a morphism of schemes. The group acts on E, and here's the action. There's a projection, and this diagram is Cartesian, and this one is a smooth and surjective. If these conditions are satisfied, then this is a principal G bundle by definition. And so I take, so the objects in this category BG are all principal G bundles over all schemes. And morphisms, well, if I have E, well, the diagram's like this, E to S, F to T. This means these are commutative diagrams where this map up there is G equivariant. Such commutative diagrams are automatically Cartesian. And the functor to S is just E maps to S. Right? Right, so this is very closely related to this example of vector bundles as families of vector spaces. You can see that. Let me just try to wrap up. So I just want to make a point here towards the end. I'll explain this in more detail tomorrow, just so you can see where this is going to go. So, so that X over S be CFG, X over S an X family, then we can define the symmetry groupoid. Of this family X over S. And the way that works is like this. In fact, you can convince yourself that the family defines a morphism from this CFG represented by S to X. And abstractly, you form the fiber product of CFGs, and there you get R. And so this is some CFG if this is representable. So then I get the general notion of a symmetry groupoid of an arbitrary object. And the definition that the family X over S is a versal family well, if first of all, the symmetry groupoid is representable, so it exists. And secondly, that the symmetry groupoid, this is it. S and T has S and T are smooth morphisms of schemes. Okay. Well, I mean, I'm assuming R and S are representable. I'm always assuming locally of finite type and all, that these are nice enough schemes. Then there's no difference between smooth and formally smooth. So. Let me say, then let me also say this is So if I have a family X sitting over S, and I have a point of S, right, then I can form the pullback, if this is maybe little s, that gives me the member of the family given by the point S. And so this family is supposed to contain all of these. Then, well, what can how do I want to say this? So if I have, in general, any algebraic groupoid, there is a corresponding CFG induced from it. I'll talk about that tomorrow. So in the case where my groupoid is actually just a group over the point, this is an example of a groupoid, then this BG, the stack of G bundles, so the CFG of G bundles, is an example of this general construction. And if this family is versal and complete in this case, in this sense, then I can construct a morphism which is just sending x, I'm sending some family y Okay, so at least that I have a definition of algebraic stack on the board before this lecture finishes. So BG is an example of an algebraic stack, and we'll see how, Well, I'm out of time, so I don't want to say anything more about this right now. Just finish here. Okay. That's it for today.